Hi, I'm Yongwoo.
And I'm Sid.
We're happy to be here to present our work, BitWhisper, enabling ad hoc, short-range walk-up and share data transmissions via surface-restricted acoustics. This work was done in collaboration with Zuyu Lee, Stephen Craig, Phoebe Welch, Chungja Shi, Thad Starner, and my advisors Gregory Abel and Shavik Das.
In the physical world, when you want to share a secret with people nearby, what do? You make sure no one else is around, you lean in and whisper. But in the digital world, sharing a secret with people nearby looks quite different. Existing solutions for secure, short-range wireless communication, like Bluetooth, require device pairing, which can be inconvenient for a number of everyday sharing tasks that require both ease of use and good enough security, such as sharing contact information with conference attendees, secure link sharing in a coffee shop meeting, etc. Also, because of the invisibility and abstractness of wireless data transfer protocols, there is no easy way for end users to ensure who may eavesdrop on their data transfer. These challenges brought us to the questions. What if we can design digital whispering that limits the scope of wireless digital communication to a visible, physical medium while enabling simple and ad hoc interactions we call walk-up and share interactions? Can we design such a system without any specialized devices or objects? Is this possible? We introduce BitWhisper, a novel, ad hoc, short-range wireless communication system that enables digital whispering. The key insight of BitWhisper is wireless data transfer is physically constrained to nearby devices co-located on a solid surface, like a table surface. That means only devices that are co-located on the physical surface can share data, while a malicious actor's devices that are not on the surface cannot eavesdrop on the surface-restricted data transfer. As shown in this video, once a transmitter transfers data, the receiver device that is co-located on the same surface successfully receives the data, while the receiver that is not co-located fails to receive it. Let me talk about BitWhisper's operation principle. We leverage two physical properties of sound to design BitWhisper. First, sound attenuates over long distances, meaning the devices that are closer are more likely to hear whispers. Second, sound is reflected from rigid physical surfaces. With that, we hypothesized that a digital whisper transmitted on a solid table would be more clear and audible for devices that are physically on the same table than for devices that are not. In order to verify this hypothesis, we ran a simulation on a software simulation tool to evaluate how sound propagation differs above a table surface. We simulated two setups: on-table setup, where a transmitter device and a receiver device are co-located on a flat surface, and off-table setup, where a transmitter device and a receiver device are placed on separate air-gapped surfaces. From the simulation, we found that the on-table receiver received almost twice as much acoustic pressure as the air-gapped receiver because of the sound reflection from the surface. Next, we empirically verified the simulated tests by running a white noise test in a lab setup. We used a transmitter device to play white noise and a receiver device to record the noise. We verified that the on-table receiver receives a stronger acoustic signal than the off-table receiver over the 18 to 22 kHz range.
Let me talk about how to implement BitWhisper. There are three key components for the implementation. First, we use inaudible and minimally perceptible acoustic signals between 18 kHz and 20 kHz that can be generated by commodity devices. Next, inspired by prior work, we use frequency shift keying method for data communication and evaluated 20 frequency channels with the frequency range. Then, among 20 channels, we found 8 usable channels for 8-bit ASCII character data transfer of BitWhisper. Lastly, any lossy communication channel must account for transmission error, and we want legitimate receivers to accurately recover lost messages while preventing adversarial receivers from doing the same. We accomplish this with a combination of 4-error correction and encryption. The 4-error correction scheme is commonly used to recover the lossy data, but if there is the limited amount of error to be corrected, 2 lossy data cannot be corrected. We use this property. As a receiver can receive stronger acoustic signals on the table than off the table, it would be likely that an adversary who would be off the table will receive lossier data than a legitimate user who will place their device on the table. This way, legitimate users can transfer the corrected data while a malicious actor cannot recover the lossy data. However, it may not be necessary for an adversary device to detect and correct all errors. Even if the intercepted message is 70% accurate, for example, J.O. blank and D blank E instead of John Doe, they may be good enough for many adversarial purposes. To address this issue, we use the encryption scheme. This way, if the adversary receives even one erroneous bit of the encrypted raw data, they will not be able to recover any of the plain text. To evaluate if BitWhisperer was effective, we wanted to answer these two questions. How robust and accurate is data transmission under BitWhisperer for legitimate use cases? And how secure is BitWhisperer against nearby eavesdroppers? To do so, we examined the data transmissions of two setups: the on-table setup that represent legitimate users' data transfer, and the off-table setup that represent an adversary who tries to access the on-table data transfer. We ran an evaluation with a wide range of parameters to replicate the BitWhisperer's data communication environments. Overall, results indicate that the further distance and wider angular displacement between a transmitter and receiver, the bigger data transmission success rate difference between the on-table and off-table setups BitWhisperer can achieve. We found that if an adversary attempts to access a legitimate user data transfer at 1 meter away and 60° to 90° angular displacement, legitimate users can securely transfer their data with BitWhisperer.
We demonstrate 3 example applications. First, users can use BitWhisperer for one-to-one data sharing like contact sharing. As shown here, 2 people can share their contact information at a coffee shop. BitWhisperer is not limited to one-to-one data sharing. BitWhisperer also allows one-to-N data sharing as well. So, users can use BitWhisperer to share a secret group chat link among a group of 2 or more users. Similarly, a user can use an authenticated device to unlock other devices that are placed on the same surface at once.
As you've seen in these applications, BitWhisperer can be deployed by repurposing an everyday material surface without any specialized hardware while enabling ad hoc, secure communication. In summary, we implemented and evaluated BitWhisperer, a novel acoustic-based ad hoc short-range wireless communication protocol that enables digital whispering. That's all for our talk. Thank you so much.